So we have this Boolean expression in the sum of products form, and we have to use a 4-variable K-map to find the minimum expression. So the way that you'd want to go about doing this, first off, you can label your K-map. So we have the W, X, Y, Z variables. So on the top we're going to have the W and the X. Y and Z on the bottom, or on the side, and label accordingly. 0, 0, 0, 1, 1, 1, 1, 0. And the same thing over here. 0, 0, 0, 1, 1, 1, and 1, 0. But how do we make sense of this expression here? And the way that you do that is with a truth table. So we're going to have 16, we have 4 variables, so we're going to have 16 binary possibilities. So we have 16 tiles in our 4-variable K-map. So we're going to have, each tile has its own number. For example, this is the 0. This is the 1. This is the 2. This is the 3. The 4, 5, 6, 7. The 8 goes over here. 9, 10, 11, 12, 13, 14, and 15. Now we list each of these numbers in our truth table here, starting with 0. So 0, 1, 2, and so on. Okay, so we have our 15 numbers. And our 4 variables, W, X, Y, and Z. And now we have to write down the binary equivalent for each one of these numbers. And this is standard for any truth table. It's just good to have the visual. For 1, we have 0, 0, 0, 1. 2, we have 0, 0, 1, 0. 0, 0, 1, 1, that's 3. And we got 4. 5. 6. We got our 7. And you can take a little shortcut if you notice these alternate. So 0, 1, 0, 1, 0, 1, 0, 1 to the end. These alternate every 2 in this row. So 0, 0, 1, 1, 0, 0, 1, 1. These are all going to be 1. These alternate every 8. And then this row alternates every 4. So 0, 0, 0, 0, and then 1, 1, 1, 1. Okay, so we have our binary equivalents. But what do we do with this expression here? So we have our function, our output here. And that's what we need to put into our K-map. So we have to translate this up here into this function. Now if you look at this function, you have W, not, Y, and Z. The W not means that it's a 0. It is off, not on. Let me write that a little lower here so it's on the screen. The Y is on. It's not complemented, so it's on, so it's a 1. Same thing with the Z. But what about the X? Well, in this case, for this part of the expression, we don't care what the X is. And that's actually a technical term in digital logic. So X can be 1 or 0. Now on the truth table you'll see, maybe if I write it out like this, so we have W not, which is 0. The X is don't care. The symbol for don't care is actually X. It's not the actual letter, it's just an X. And then we have Y and Z are 1. Those are both on. So that's what the binary looks like for this part of the expression. So we have 0, don't care, 1, 1. Okay. Now if we look down this truth table to all of the possibilities that start with 0 and end with 1, 1, we're going to notice that there's going to be 2 of them. So we're going to put a 1 here for each of those 2. So let's do that. I got a different color for that. So starting with 0 and ending with 1, 1. But we don't care about what X is. So we have this one here, 0, 0, 1, 1. And we're looking for 0, 1, 1, 1. So 0, 1, 1, 1. That's the 7. To give you a preview of what I'm doing here, we have the 3 and the 7. So over on the K-map, those are going to be marked as on. And we're going to go through and do that for the rest of the expression here. So again, we have X, Y, not Z. That's a 1, 0, 1. You'll notice we don't have a W. The W is don't care. So this expression starts with, or this part of the expression starts with don't care. X is 1. Y is 0. Z is 1. So we're looking for 1, 1, 0, 1 and 0, 1, 0, 1. So 0, 1, 0, 1. We have it right here. And 1, 1, 0, 1 is down here, 1, 1, 0, 1. And I'll transfer this over to the K-map once I'm done. Actually, I'll do it as we go. So we have 5 and a 13 there. So 5 and 13. Sweet. For the WY, so W, no X, Y, and no Z. These are both on. The W is 1. The X's don't care because it's not there. The Y is on. The Z is don't care. So we're looking for 4 different numbers here. 1, 0, 1, 0, and so on. So let's find all the possibilities with the 1 and the 1 in the W column and the Y column. So looking down here, 1 and 1. We have a 1 and 1 here. One and 1. 1 and 1 down here. And a 1 and 1 down here. That's 4 possibilities. Okay. This one's easy because we're not missing anything. On, off, off. right? On, off, off. That's what we're looking for here. 1, 1, 0, 0. So come down to 1, 1, 0, 0. And there it is. Mark that. I forgot to mark these on the K-map, but I'll go and do it afterward. Next one, we have both ones, both on. W, no X, no Y, and Z is on. So that's 1, don't care, 1. So we're looking for all the possibilities with 1 at each end. So here's 1. 1, 0, 0, 1. Again, we have the 1s at the end here. We don't care about the center. We don't care about these two bits here. And then all the others with the 1s at the end are already marked. So we're just going to move on to the next one. We have X, Y, Z naught. So that's on, and that's off. There is no W, so W is don't care. We don't care about it. We don't care if it's 1 or 0. The X is 1, Y is 1, Z is 0. So we're looking for anything that ends with 1, 1, 0. So let's look down the column here, 1, 1, 0. Got one right here, 1, 1, 0. And that's it. That's the end of our expression. So that means that anything that wasn't marked is going to be a 0. It's off. And in the same way that we're marking those with zeros, they're going to be marked 0 on the K-map. So we have 0, 1, and 2 are zeros. 4 is 0. 5 is on. 6 is on. Then we've got 7. Oh, we already marked that. Then to 8. Off. And the rest are 1s. Okay. Now that we've got our truth table transferred over to the K-map, we need to make sense of the data in the K-map. We need to group these ones together in the most efficient manner to get the best answer. Again, we can only take these certain ways. We can take them like this. Change color here. And just because I'm doing this doesn't mean that I'm actually going to do it that way, because you want to take them, you want to take the groups, you want to take as many ones as possible at the same time. For example, this. Assuming that you already have some K-map experience, but if you forgot, we can take them like this. We can take them like this. We can take them like this. We can take them in 2. We could take them in 8 if we had 8 together. We could take them in 16 if we had 16 together. We can take them in 4 in a row. Both ways here. If we had all 4 corners, we could take those. But unfortunately, we don't. And we're limited. So we're going to have to take this row here, or this column, take this entire row, and then we're going to take 4 squares I can see. So 1 here, 2 here, 3 here, 4 here. So our minimum expression is actually going to have 6 parts to it. So we're not minimizing it, but we're likely going to get rid of a lot of NOT gates. So I'm going to do this by color here. to be as clean as possible, clean and organized as possible. So for the first one here, I'll do this one in red. Oop, don't want to do that. Let's see. Let's try this. That's better. Okay. So how do we translate this into an expression? Again, I'm assuming that you have some K-map experience, but if you forgot, we have this means W naught X naught. This means W naught X. This is WX, and this is WX naught. On the other side, we have 0, 0, which is Y naught Z naught. 0, 1, which is Y naught Z. 1, 1, it's YZ. 1, 0 is YZ naught. Okay. So the way that you take this expression is, or the way that you take this column here is the WX column. The W is not changing. I should have started with a different one. Let's start with a different one here. Let's start with this square here. For this square here, you'll see, if I can get this together here, I'm getting it together. Comparing the W's, they change. Over here in this column, it's W naught. In this column, it's W. Since they change, we are not going to include that in our expression. These, the X's, we have X and X, they don't change. So that's going to be part of the expression. So I'll write it over here. So for our first one, this square here, I'll write it in green. We're going to have W's changing, that's not there. X is not changing, so X is going to be included. So we have X. And then on this side, Y is changing, and Z is not changing. So Y is going to be excluded, Z is going to be there. So we have XZ. XZ. Maybe I'll just put it down at the bottom. So XZ is our first expression, or our first part of the expression. This part here, in the red, we have WX. They never change on this entire column. So we're going to have WX. And on this side, you'll see that the Y changes and the Z also changes. So both of those are actually going to be excluded from this expression, or this part of the expression. I keep on saying expression, and I don't mean the entire answer. I just mean this one little section here. This one little product. For our next, we're going to take this row here and try to draw that a little better. the y and the z don't change in this entire row. So yz. The w changes, the w naught changes, the x changes, and the x naught changes. So they're all going to be excluded from this part. And that's it for that. I guess I'll switch over to orange here. We're going to take another square. We have 3 more squares to take here. So we'll take this one here. W stays the same, x changes. Y changes, z stays the same. Simple. For the next, we take this square here. We want to take the maximum number of ones that we can. We can take them in 2s if we wanted. We can take them by themselves. But in order to get the minimum expression, you need to take them as many as you can together as possible in 1, 2, 4, 8, 16, and so on. So for this expression, you'll see w changes, x does not. So x that's too light. So x, and then on this side, y stays the same, z changes. So y. We have one more square. For this one, again, w stays the same, x changes. So we have w, and on this side, y stays the same, z changes. So y. So all said and done, this here at the bottom is our final answer. The minimum expression that we can take, or the minimum using Boolean algebra or any other method, this would be the minimum expression that you could reduce this up here to, and that would be the final answer.